So the final section in our unit on stoichiometry is looking at percent yield, percent purity, and a little bit of the actual applications of everything we've been doing. So what percent yield is really just how much did you get compared to how much you should have got based on what your limiting reactant was. That's the idea. So when we do calculations in stoichiometry and determine how much of a product we get given the limiting reactant, that is our theoretical yield. When we do experiment and we filter something through gravimetric analysis or another method, that will be our experimental yield. And we've done both of those already throughout our course. Generally, when we're talking about things that are going to affect your yield or lower your yield, where ideally it's 100%, is if you're doing a reaction and there are some side reactions happening called competing reactions. So some of your reactant is being consumed to create the product you want, but some is actually being used to do something else that you didn't intend. Sometimes when we buy a compound, the purity of the compound is not actually 100%. We will buy 99, 98%, or sometimes less if we're just using an everyday object, like when we use steel wool for that single replacement reaction to create copper back in one of our first labs. Inaccuracies in measurement, which I'm terming here as random error, would be things that we should be able to correct for if we are constantly doing multiple trials in our experiment, and we try and do that in some experiments, but it really depends on what the focus is. Inaccuracies in measurement sometimes is just about care, sometimes it is skill as well. And finally, we've seen transfer loss for sure. That is when you are trying to collect a solid and you just can't get it all out of the beaker. Onto the filter paper would be a good example of that. And again, we saw that in lab number 2 when we were doing the lab with the steel wool. So calculating percent yield, we use this equation. Percent yield is equal to actual yield over theoretical yield. Your actual yield is from your experiment. Your theoretical yield is from a calculation. So generally when we're talking about a limiting reactant calculation. So this is usually what you actually weigh in the experiment, and this is done through calculation. It's what your theoretical yield is. You can turn it into a percent. So not a lot of doing those calculations yet. We focused on that already in limiting reactants. So let's look at this question. Ammonia can be prepared by reacting nitrogen gas taken from our atmosphere with hydrogen gas. When 7.5 grams of nitrogen reacts with sufficient oxygen, the theoretical yield of ammonia is 9.1 grams. So again, this would be from a calculation. If 1.72 grams of ammonia is obtained by experiment, what is the percent yield? So percent yield is your actual or experimental over your theoretical times 100. So our actual is 1.72 grams, our theoretical is 9.10 grams. Times 100%. So 1.72 divided by 9.10 times 100 equals 18.9%. I only have 2 digits with nitrogen, but I didn't actually use that in the calculation anywhere. The other ones I have 3. So that is my final answer. So in this experiment, we would have 18.9% yield. The only thing that probably adds to this is making sure that you know what your theoretical yield is. So actually being able to arrive at the 9.1 grams. But we've done that calculation many times. So we're going to continue and have a look at a couple of these applications. So percentage yield, when we start looking at career fields and places where chemistry is actually being used, it is really, really important. If we're talking about a chemist who is doing research to try and develop a new type of drug, a new type of medicine for any disease or disorder, they might just be interested in actually being able to make the molecule itself. They don't necessarily want to make it so they can produce mass quantities for a factory. Once we know that we can make something where the percent yield doesn't really matter if you're just looking to see if you can make any of it at all. So 1% yield is great if you're just trying to make a little bit of it. But once you're trying to actually produce it to make money for business, for doing an actual run of medicine, when that happens, then yields really matter, because the higher the yield, the more efficient their process is, the more efficient the industrial process is, the less money they're losing to wasted reactants, in other words. So if you buy 10 grams of reactants and you're hoping to get 10 grams of products out of it, anything that you don't get out of that product, if you only get 7 grams, then you're only ending up with a 70% yield, or 30% of your product has gone missing, and that leads to what we call profit loss. So one of the big challenges that we face in chemistry is dealing with impurities, and sometimes if our reactants aren't pure, and we operate from, a lot of times in chemistry, from the idea that what we're using is actually completely pure, and that's not always true. The steel wool example we did in class, when we put that into copper sulfate to create copper and aluminum sulfate, the steel wool had probably some dirt on it. It probably had some other impurities into it. So it wasn't 100% iron, and that definitely affects our results. But if we know about it, it's generally okay. So imagine that you had added 1 gram of sodium, but the sample of sodium was only 98% pure. Then you actually only added 0.98 grams of the sodium and 0.02 grams of impurities. So basically, if you think your limiting reactant was 1 gram, but it was only 0.98 grams, you have just built in a little bit of error. The percentage purity of a sample describes what proportion by mass of the sample is composed of a specific compound or element. For example, suppose that the sample of gold has a percent purity of 67%. That would mean a 100-gram sample of the sample would be 67 grams of gold and 33 grams of impurity. So we're going to try and apply this. This is a wordy question, but it will stand to help us understand. Iron pyrite is known as fool's gold because it looks similar to gold but is actually worthless. Suppose you have a 13.9 gram sample of impure iron pyrite. You heat the sample in air to produce iron 3 oxide and sulfur dioxide. So the equation's there and it is balanced. So from this experiment, we collect 8.02 grams of iron oxide. So we have 8.02 grams of this. What was the percentage of iron pyrite in the original sample? Well, first of all, if we're reacting something with air, we know that this is going to be our excess reactant in this particular case, and that makes this the limiting reactant, which is fine. What we need to do is we need to figure out, if we have this many grams of this compound, how many grams of iron pyrite do we actually have? So I'm going to start with my product. I have 8.2 grams Fe2O3. So we're going to turn it to this, just doing our stoichiometry. So step 1 was done. 1 mole of iron 2 oxide. We need a formula weight here. So 55.845 times 2 plus 3 times 15.999 is 159.687. So step 2, convert to moles. Apply the ratio, so I want iron pyrite. So I use the 4 mole to 2 moles of whatever was here. Step 3, step 4, convert back to grams. So 55.845 plus 2 times 32, 69.845 grams. Let's correct that. 55.845 plus 2 times 32, there's 2 sulfur in there, is 119.845 grams. So we go through and do our calculation. 8.02 divided by 159.687 times 4 divided by 2 times 119.845. So if that was my amount of product collected, that must have been what the limiting reactant was, or the iron pyrite was. So now when we do percent purity, that is equal to the actual mass divided by the mass of the sample times 100. So I got 12.04 grams of iron pyrite. I had a sample of 13.9 grams of sample. The sample would have been 86.6% pure. So by using what our product was determined to be, we can using what our product was determined to be, we can figure out what the mass of the reactant was, and compare that to the mass of our sample, which we can then figure out what the purity is. So we have a couple of practice questions here. It says the following reaction proceeds with 70% yield. So C6H6 liquid plus HNO3 gives me C6H5NO2 liquid plus water. So the question says calculate the mass expected if this is a 70% yield reaction. So I have that to start with. 12.8 grams of benzene, C6H6. Convert to moles. Let's see if we can get this right this time. C6H6, so we convert to moles. Apply the ratio. Now I need a molar mass again. So 6 times 12 plus 5.05 plus 14 plus 32. C6H5NO2 over 1 mole. So balance the equation, convert to moles, apply the ratio, convert to grams in this case. So we go through 12.8 divided by 78 times 123.11 is 20.2 grams. It's only a 70% yield, so we multiply by 0.70 or 70% in decimal form. There's our answer. So this would be 70% of the expected product at 20.2 grams. So the next question is pretty much similar, except they don't have the equation written out for you. So it says when calcium carbonate reacts with hydrochloric acid, it forms calcium chloride plus carbon dioxide plus H2O, 2 chlorides will balance. So when we do this, we have to read this question now. It says if the reaction occurs with an 81.5% yield, so that's the step we did up here in red, what volume of carbon dioxide at STP will be collected if 15.7 grams of calcium carbonate is added? So there's our starting material. So we go through our steps. Step 1. Apply the ratio. It's 1 to 1. And then to volume. And of course, this is at STP, or standard temperature and pressure. So 15.7 divided by 100 times 22.4 is 3.52 liters of CO2. 3.52 liters CO2. Now our yield is 81.5. So times 0.815 is 2.87 liters CO2 is expected. So our final question is looking at a purity sample. It says an impure sample of silver nitrate has a mass of 0.340. So that's what we actually have. So we treat it with hydrochloric acid to get silver chloride and nitric acid. Silver chloride is filtered and any remaining chloride is washed away. The silver chloride is dried and weighed and found to be 0.231 grams. What mass of silver nitrate was obtained in the original impure sample? So 0.231 grams. It's the silver chloride, so it's this. The molar mass of silver chloride is 107.87 plus 35.45 is 143.32 grams. Apply the ratio. 1 mole of silver nitrate for 1 mole of silver chloride. And then we need the molar mass of silver nitrate. So 1 silver atom is 107.87 plus 14 for nitrogen plus 3 times 16. So 169.87 grams of silver nitrate for every 1 mole. So balanced equation, convert to moles, apply the ratio back to whatever unit we need. So 0.231 divided by 143.32 times 1 over 1 times 169.87 equals 0.274 grams of silver nitrate. So there must have been 0.274 grams of silver nitrate in that sample. Percent purity in this case is going to be equal to 0.274 grams, the mass I actually got, divided by the mass of the sample, times 100. Equals 80.5% pure. And that is essentially the topics that we need to look at with percent yield. The big thing is calculating yields, which we've done a bunch in the labs, but also looking